On va commencer. Bienvenue au 19e Meetup Computer Vision Paris. So I'm going to switch to English because today both our speakers are going to talk in English. So today we have two talks. First, we'll have Oleksandr and Nazar from Pressed AI, who will talk about an algorithm they did to track ball in a foosball table. And then we have Aloysio from Kernel Technology, who will present us segmentation algorithms to improve annotation tools. So let's start. So Oleksandr, Nazar, are you ready?
Yes. Yes. So
Perfect.
I will share a screen. Okay, let's go.
Do you hear me well?
Yeah, that's good.
Yeah, that's nice. Hello, everyone. We are Team Pressed, and it's a great pleasure to see all of you here. We would like to share some details of the algorithm and of the overall system of our one of our latest projects. It's called Foosball Table 2.0. And when it comes to foosball table, are you a player, a spectator, or a referee? Actually, it's not an easy task, as it could be extremely difficult for human eyes to keep tracking fast balls. And our team developed an event detection system for a foosball table for the Foosball Society. And this society unites thousands of professionals and amateur players around the 21st century version of foosball table. Now we are going to share with you some details of the implementation. So let's go.
At the beginning, let's watch a small reportage of French TV about the first generation of table football.
Okay, let's watch.
Un but à 14 km/h, vitesse de balle, nombre de victoires et de défaites, classement, tout est enregistré. Ce baby-foot est connecté.
Voir les temps forts et les stats du match.
Aux quatre coins de la table de jeu, plus de cendriers, mais des QR codes à flasher avant de démarrer une partie pour accéder à une application sur leur téléphone.
Là, on a le score au milieu du baby-foot, on a le ralenti qui apparaît sur la télé.
Grâce à cette caméra suspendue au-dessus, impossible désormais de contester une gamelle ou de ne pas voir une roulette.
On ne peut plus tricher. Déjà, il y a un arbitre, il y a de la vidéo, et il y a des statistiques. Nous, on aime bien aussi faire des tournois, faire des compétitions et afficher, c'est nous les champions du hub de la plateforme.
Dans ces univers de travail pour les startups, le baby-foot 2.0 a trouvé une seconde jeunesse.
L'idée, c'est d'allier la tradition et le modernisme actuel, donc la connectivité, la fédération de communautés.
Okay, so our customer had well-defined requests. And first of all, the idea was to move from the sensors to the camera. For the first generation, they used two optical sensors in the cages, pressure sensor at the bottom of the cage and contact sensor on the side of the table. And this switching will help to reduce the cost and increase the accuracy of the event detection. Secondly, moving to computer vision solution, it helps to collect more relevant information about the game in general, about some interesting statistics of the players and behavior, the ball on the table. And finally, to increase stability, robustness, and user experience in general, it was decided to move from the cloud to local computing to prevent some network issues and be more stable in general. Next slide, please. So for this project, Presta team defined and wanted to emphasize some specifications of this project. First of all, we wanted to notice that to detect ball on a high speed, more than 30 kilometers per hour, we need at least 100 frames processing. That's why we choose 120 FPS camera for this project. As you know, for computer vision tasks, it's extremely important to deal with different lighting conditions. And also for this project, we choose a lens with a minimal distortion because geometry of the field plays important role too. As we are going to move to local computing, we found a compact and powerful devices as Jetson Nano or Jetson Xavier, and we will explain a little bit more in the next slides. And also during the game, the table shakes, so it's important to deal with stability issues of the table. Next slide, please. So our main focus on this project was to detect events like goals in outs and measure their speed. Of course, you know what is a goal, but what is an out? So basically, it's an event when ball goes fast into the cage and at 1 second or even less comes back to the field and doesn't fall into the cage. And it's extremely important to distinguish between these two events because we can apply different rules how to count this event. So that's why we deal with this. Next slide. Now we want to show you a small demo video of our final solution. You can see professional players playing a match. Standard match is up to 5 goals. You can see detection of the ball and trajectory. Its last 20 position in the trajectory. Actually, for event detector, we collect more. Now you have just seen an event. It was in out, so the ball was super fast. And we counted with a green score at the bottom. And the yellow score is for original goals, ordinary goals. You may wonder if video is accelerated, but it's not. It's video of the game, of the professionals. And maybe we can have some freezes because of internet. As you can see, at some point, we even cannot see the ball because player cover it by itself. Let's see one more event and we will move on. You also can see how tables shakes during the game. And during this event, you also saw a speed of the ball. I guess it's enough.
Okay, let's move on.
Yep.
So now ball is on my side, and will tell you a little bit about the data set and about the corner cases that we faced. So the data set at the beginning was pretty small. We tried to work with that, but once we discovered new corner cases, we had to do you hear me?
Yes, we hear you.
Yes, we can hear you. We can hear you.
Once we discovered new corner cases, we had to gather new data to cover these corner cases. So in the end, we had like 12,000 images in a training data set plus data augmentation. In the validation set, we had 3,000 images, and in the test set, we also had 3,000 images. All of this is for a neural network. And also we had a specific validation data set for event detection. And it consists of 10 videos of professional gamers and professional players, which are much more complicated, and 18 videos of amateur games. So in total, we've got like 220 events with goals and in-outs. So in-outs are really complicated to get, and that's why there are not so many of them, but that's enough. Okay, so and also for this validation data set, as we had to measure ball speed as well, but we cannot be sure that speed estimated by sensors is very like exact and precise. And as well for our algorithm, we had to find a way to estimate the real speed of the ball, and that's why we just used a ruler and a computer screen and computed distances pixel by pixel. So these were our ground truth. Okay, let's move on. So here we'll show you several examples of corner cases. So this is the first one, and it's actually the most interesting one, because when a ball is very fast, we can get these kind of images, and even considering the fact that the FPS of the camera is 120, even in that case, the ball is very blurred, and it looks more like a rectangle than a ball, actually. So it changes its shape. Another one is when players are moving very fast, and in that case, the model could could mix and think that a player is actually the ball, even if a ball is visible, like on this picture. Another one, pain in the neck, is like hands and different parts of the body on the table, like neck or a head, arms, etc. Because the color of body skin is very similar to a ball, and that's why often, depending on a lighting, this could be misunderstood by a model as well. Okay, and this corner case is about extreme conditions. It's probably sunset, and the light has a specific angle, and as you can see, ball is almost white, but it doesn't supposed to be like that. And it also was important to have these kind of images in our training data set, as we discovered during the training and estimation process. This one, as you can see, is really hard even for a human eye to see a ball in this picture, but it exists, as you can see here. So it was also a challenge for us, and we had to add a lot of images like this to be able to detect ball and not to miss it. Okay, so we had a pretty long path to the final algorithm, and we've tried a lot of different things because the problem itself is very challenging to get like accuracy higher than 95% with FPS of 120 and with local computing on a local device. So first of all, for a prototype, we tried a pure classical CV algorithm, which consisted of edges detection and like circle detection. It works somehow, but of course it's not the state of the art right now, but it was good for a prototype. Then we also thought that background estimation and removal can work because we have a static camera and a static table, but it was not accurate enough, and the table actually is not so static, as we discovered later, especially when professional play, because it shakes, as Nazar showed on one of the previous slides. So then we went to like a classical approach of the object detection network. We just tried a network from neural network zoo, and trying to fine tune it on our data set, but it was too slow and not accurate enough. And we had a lot of false positives, etc. So we moved to our current model, which we will explain more in details on next slides. And we tried just to directly detect ball on every frame. Unfortunately, it wasn't fast enough. So the performance could be better. That's why we had to try some other approaches. Just we tried to mix different algorithms like tracking, neural network classifier. So the idea was to detect a ball and then apply some simple tracking algorithm like min shift or cam shift, and then to check validity, validate it by a neural network classifier, which has to have like extremely high accuracy. It worked well, but because of the specifics of Jetson devices, it wasn't fast enough because the program has to switch between one algorithm, then another one, between CPU, GPU, etc. So it was rather slow, but faster than pure neural network. And then what also didn't work well is Jetson Nano, because it's just not powerful enough for 120 FPS. Okay. So this is what we have in the end, and this is the pipeline of our algorithm. So first of all, we take frames from the MyPy camera, then we decode, and Jetson devices have special engines for decoding, so it's not an issue at all. It's not a performance issue. Then we go to frame preprocessing, like sizing, cropping, etc. Then we also invented a trick of motion detection in a specific region of interest. As you can see on this slide, there are these blue rectangles, and they are our actual region of interest because they are located next to the cages, and the most interesting stuff always happens next to the cages, as you suppose. So we cropped these regions and then applied the simplest motion detection approach, which is just frame difference. It's extremely fast and it doesn't take much memory, but it works pretty well because we needed it only for optimization purposes. So we didn't care if there are some false positives, but we don't have false negatives, and that was the most important thing here. So then, if and another trick is if motion in this region of interest is not detected, in that case we process only a single frame in 5, so 1 of 5. For example, if it's the first frame, we go here. If it's but there is no motion. If it's second frame and there is no motion, we just skip it. We compute motion and then skip it, and till the 6th frame, for example. If the motion is detected, disregarding which frame it is, we try to detect ball. Okay, so if we apply our model, detect the ball, just apply some geometric filtering for bounded box, and then move to tracking. For tracking, we have a state machine and with some heuristics and Kalman filter. So we decide to add or not to add the current ball position to our track. So, and when if the ball is added, then we move to event detection, and depending on the motion between the states, we decide if it's a goal, if it's an in-out, or there is no event at all. Also, we had a feature of saving replays and of computation of game statistics like ball speed measurement, etc. And then we save. If an event happened, we save all the data to Jetson, to JSON, and we save also a replay of 5 seconds. 4 seconds before an event and 1 second after an event. Okay, Nazar?
Okay, so could you guess what model we finally used in our solution? You can write down on the comment, or let's wait 30 seconds. Any ideas? see YOLO.
I know the answer, so I will not.
Sorry, I didn't hear you.
Okay, let's move on and conjure you. Alexander, next slide, please.
We can't see the slides anymore.
Yep.
So you can continue guessing what model we applied to our solution.
Okay, sorry, I had some issues.
Yeah, that's good. We can see it.
Thanks. Sorry. But you heard everything that I said, right?
Yeah, yeah.
Ah, okay. That's nice. Okay, so we can move.
Yes. Of course, the first idea is to use the YOLO just because it's very popular way on ears, but unfortunately, it doesn't work well in our case. Next slide, please. It may be surprising, but we use a segmentation model for ball detection. We decided to use a really basic and light architecture like UNet. We just modified it for our image size and ratios. And for this project, we worked on TensorFlow 1.15 and just created a graph of operations, which is like TF model here. It's just operation of convolution, multiplications. All you need is just API calls, and it's really good for transfer learning, for architecture modification, and for training in general. But as you can see, the performance of pure TensorFlow model is quite low. So we started with 16 FPS on Jetson Nano and 37 FPS on Jetson Xavier, which is definitely was not our goal. That's why we were trying to optimize inference for this model. Next slide, please. And we were really lucky, and everybody who tried to use Nvidia Tensor Rt framework are lucky, because it's a great accelerator to optimize neural network inference. This Tensor Rt just reorganize your model in the way to make advantages of highly optimized GPU operation and reduce the size of your model, memory, and etc. So I will explain what Tensor Rt can do. So first of all, it can do kernel fusion, and it exists two versions, vertical and horizontal fusion. For example, a few consecutive operations can be organized together and used as one block of operation. And in this case, we will use some highly optimized GPU algorithm, or it can be the same kernel but with different weights. In this case, Tensor Rt also organize it in one block, and this helps to reduce latency and increase throughput for the model. The next operation which is available for Tensor Rt is precision calibration. We can choose the precision for the model weights from float 64 until int4 even, but not all devices support this precision. For example, for Jetson Nano, it's only float 16 which is available, and for Jetson Xavier it's int8. And but when you do this calibration, you reduce the size of the model, I mean weights, and you can lose a little bit of the performance, initial performance you had, but with the algorithm of calibration, you need to apply this algorithm to save your performance, and actually in the worst case your performance can degrade less than 2% or even 1%. In our case it was less than 1%, but for this calibration you need to use all data you used for the training. So the next is kernel auto-tuning. It's as I said, low-level algorithm for GPU operations. And the two next option is dynamic tensor memory and multi-stream execution, which also helps to accelerate our model. So, but you can ask what is the difference between TF-TRT model and TRT engine. So TF-TRT model is actually integration of TensorFlow ecosystem with Nvidia Tensor Rt framework, and it takes all advantages of the Tensor Rt if this execution exists for specific layer of the network. If not, we will return back to frozen graph and use a standard TensorFlow operation. So it helps to accelerate your model, but it doesn't make it super as fast as it could. If you want to get the better performance, you need to optimize to convert your model to Tensor Rt engine. And in this case, you only need to apply 3 simple steps for the first look. It's like super easy. It's just to convert, save, and use this engine. But during these steps, there is some pain. So first of all, there is 3 ways to how to convert model and prepare it for converting. We need to first, we can use Python, either Python or C++ API, and reconstruct from the scratch model architecture, and be sure that weights representing in the file corresponding to the architecture. It's quite tricky. And there is another option, is to save our frozen graph and using special parser, which is provided by Nvidia, and convert it to Tensor Rt engine. Actually, and one remark on it, if your model contains some layers which are not supported in Tensor Rt, you have 2 options. You either need to redefine your architecture from the beginning, or implement this layer manually, and it will work. So we convert our model to Tensor Rt with a special tool, and then we need just to integrate. It's really easy. There is a lot of examples and great tutorials from Nvidia. And as you can see, performance of our network and solution in general just increased in 4 times almost for Jetson, Xavier, and X. And at the end, we have like 115 FPS for pure, if we apply pure model on every frame. But as you know already, we apply some heuristics just to have room for future features. And as we tested, there is no really big advantages of using this network on every frame. And if you want to know more about this trick optimization with Tensor Rt, of course, you can use documentation, or you can go to our blog posts on our website and check them, because we described in a few articles how to do this Tensor TF-TRT optimization and TRT optimization. So we can go to next slide.
Okay, yep, and we have the first part of the blog, and we're going to post others in the future as well. Okay, so now we almost came to the finish, and here you can see metrics, final metrics actually of ball detection. This is this is about the neural network itself. So F1 score is 97%, which is pretty good, and mean error. This is the mean average error for a center of a bounding box of a ball. So it's 1.6 pixels, which is really good. So here we also have just intermediary results for comparison of sensors solution and our CV solution. It's not the final one, because at some point we have seen that CV works better, and we just stopped comparing them. But as you can see, recall was the same, but sensors had a lot of false positives, and that's mainly because of some hands on the table. So the precision wasn't perfect for sensors, but it was perfect for CV. And speed estimation was a little bit better for computer vision at that time. So both estimations and measurements are pretty good. So, and these are the main numbers. This is precision and recall of event detection on the validation data set that we presented in the middle of the presentation. So precision is 99%, recall is 99%, and F1 score is 99%. So it's we had like only 2 false negatives, only 2 false positives, and we also tested it on the live games of amateurs and professionals, and these numbers are the same, I would say. So everyone was happy. So Nazar, I let you finish.
Okay, so finally, we was able to reduce the cost of the solution, because sensor solution with sensor cost around 2,000 euros, and as you saw from the previous slide, device camera an installation now costs around 500 euros. Also, we greatly simplified installation process, and of course the process of updating and supporting solution becomes simple. We increase higher accuracy and added options to apply custom rules or change rules from the game to the game, because for this game we can use some professional rules of counting goals, and in the bar you will use another rules. So this is really cool. And also custom statistics, just to have more fun and be more involved in the process of the game. It's also done. So that's it. Our presentation is finished. Thank you for attention, and waiting for your questions.
Thank you very much. We are glad to be here.
Thank you for the great job. So I think we have a question in the talk about the position of the cameras.
Yes.
So
yes.
Can you see it?
Zane. Yeah, so as I wrote, the camera was placed just about the center of the table, of the field of the table, in a height around 1.5 meters. And because we use low distortion camera, that's why we see such kind of image.
Okay.
Is it good now?
I think we have a question here.
Yeah. Hello.
Hello.
Just a question about the first segment of your pipeline, the whole structure of it. Was that purely experimental, or was there something you based your pipeline on? I mean, what was the intuition behind that? Thank you. I mean, yeah, I mean, just for the parameters, for example, you mentioned that you chose the 5th frame as some kind of threshold to see if you would still consider, well, let's say, including the frame in the pipeline, or just ignore it. Like this is just one little example, but I mean, just all the whole pipeline, was that purely experimental, or did you have like some other experience that you started from, or was that mainly from scratch and it depended on your exact use case?
It's not from scratch, because it's based on our experience in different projects. So this thing with optimization based on motion detection is quite a common one. It's probably used in a lot of places and in a lot of algorithms. About the 5th frame, that was intuitive to skip some frames. Mm-hmm. But the numbers of frame to skip, we computed experimentally to choose the best speed and at the same time the best accuracy. Because if we skip, for example, only 3 frames or 2 frames, accuracy keeps to be the same.
Okay.
So okay, if we skip 5 frames, in that case, accuracy just is lower.
Okay. Okay, I see. Thank you. Thank you.
There is another question. Is there any interlacing between frames? It's in the chat, actually.
Okay. What do they mean by interlacing? It's
I think, Eric, if you are here, I think you can unmute yourself and.
Yes. Good evening. Thanks for the work. Usually, in some video recordings, there is interlacing. It means that one lines out of two is renew, for instance, the odd lines, then on the next frame, the even lines. So to have a total renewal of all the pixels, you have to wait for 2 frames. So do you have all new pixels at every frame, or one lines out of two only refreshed at every frame?
We have a new frame each time. Every time we have a new frame, totally new. We grab frames from the camera, and every time it's new, it's motion, it's JPEG format.
Just to add, because of these devices, Jetson devices actually have special hardware for decoding. It becomes easier to grab frame really fast, not loading CPU, and decode it on the fly. So that's why, yeah, as Oleksandr said, yes, we have every new frames every time.
Yep.
Thank you.
So, and from camera, we have motion and JPEG frames, like images, and then they are decoded by a specific engine inside Jetson. So each frame is absolutely new.
Okay. We have another question from Sonia, and then I think we have to move on. It's in the chat.
Yes. Okay, so the first question, yes, we have tried different architectures. Like we tried detectors, we tried MobileNet, SSD, but actually we saw that segmentation just worked better at the data we had. So we concentrated on the segmentation model and trying to optimize and improve and train it more, as also it requires less data. In general, this unite models requires less data to train. So about the resolution, it's 400 by 200 pixels. And the last question, so all these corner cases when the ball were really blurry and like have oval form, we added to the training set a lot of these examples. That's why segmentation model was able to detect even these blurry balls when detectors failed. Thank you for your question.
Yeah.
And for the last question, there is no such kind of integrate. I will repeat the question. Do you know if equivalent of TRT exists for PyTorch? There is no such kind of integration between like TensorFlow, Tensor Rt, but definitely you can just save and convert your model with Python API. You can convert it to some intermediate file like ONX or FTP formats, for example, and then use a parser provided again by Nvidia and optimize your model. So there is no actually any constraints about framework to use. You can use TensorFlow, PyTorch, Kafka. Cafe, sorry.
Yeah, and the TRT doesn't depend on TensorFlow or vice versa. it's a engine for Nvidia. So.
Okay.
Yeah,
Thank you, guys.
And one last word about Tensor Rt to finish, because I forgot to mention it.
Yep.
It's hardware dependent. So if you cannot create your model on one device and move it to the other, you need to optimize it every time on the new device. So be careful with it. If your model doesn't work on a new device, it's logical. You need to re-optimize it, rebuild it.
Thank you, guys. Thank you again. It was awesome. And now I think we'll switch to Aloysio.
Okay.
Thank you.
Thank you.
Thank you. Yeah.
Can you all see me and hear me? Or can someone?
Yes.
Yep.
Okay.
You see.
So my name is Aloysio. I'm a software engineering at Kernel Technology. It's a data annotation platform. So we are always trying to make new kinds of making annotation easier and faster. So interactive segmentation is a way to make image segmentation faster. So today I will talk about why to use that. Make a small demo just to make an introduction. Then I'll talk about performance, how to measure it. And finally, I'll talk about the model. And in the end, something else that we can do if we use interactive segmentation. So let's start. So first, image segmentation. Basically, the idea of image segmentation is giving a class to each pixel of an image. So here we have a car, and it is an image. It has lots of pixels, and we want to select the car. If we want to segment the image of the car, we just select every pixel that has the car. So here we have a segmentation mask for the car. So just a quick reminder. So why to use interactive segmentation? We've seen the car. So if you want to make a mask for the car, you usually are going to draw this mask by hand. And if you want to draw something by hand, you are going to use a computer. And computers usually have mouses. And it's very hard to draw a contour with a mouse because it's not optimized for that. You're actually going to, if you want to do it fast, you're going to need a specific hardware for that. For example, a stylus pen. What's good for mouses? Clicking. So if you can segment an image by just clicking, you are in the best possible world. So the idea is try to segment images by clicking. So in interactive segmentation, you're going to click in the car, and it's going to select automatically the image using an algorithm. Another important thing to mention is also that if you concentrate just in selecting the car, you're not going to waste your time trying to draw perfect outlines. And that's something that's very hard for a human to do and can actually extend the process of segmenting the image. So now a demo, that's Kylie's platform for image annotation. So first here, we make some points. So you can annotate the car using points. You can also draw lines. You can draw bounding boxes. And you can make an image segmentation using our superpixel tool. Superpixels are not very good for great big images like this car because they don't define like good edges for the wheels here, for example. They are very good for annotating small objects, and you can't change the edges easily. You're going to have to redraw them then by hand. Using the indirect segmentation tool, you actually are just going to click, and if it made some wrong selection, you can correct it using the indirect segmentation tool. So here, click is in the middle of the car, it selected the whole car. But if you want to make corrections, you can do using the indirect segmentation tool. So a better example will be showing clicking the street here. We click here, we see that the selection is not very good. If you add other points, you can refine the selection. You can actually do also negative points to
further refine the edges. So you can interactively make the selection using just the interactive segmentation tool. It's something that you can't do with super pixels, for example. Next slide. So coming back to our last example, here we had a car, and we wanted to segment the car. If you use the interactive segmentation tool, what you're going to do is you're going to add positive clicks and negative clicks, and somehow we're going to input this information to a model, and then the model is going to generate this segmentation mask here. So we're going to add positive clicks in the middle of the car and negative clicks wherever it made a wrong selection. Always interacting with the model. So it's a sequence of clicks. So how to measure performance? So what we do usually in image segmentation is use intersecting over union. But what we have to add here is that we have the number of clicks. So there are two important metrics: is the number of clicks at X%. So is the number of clicks to obtain X% of ERU, and the ERU obtained with a given number of clicks. So for example, 5 clicks, I get 80% ERU. And normally we do the average in the whole data set. So talking a little about the state of the art, what models do in general is that we have a neural network, you have the image, so the image is an input, of course, and you have the input of the embeddings to the network. And what's usually done is the embeddings for the points are just a single channel image. And we have a channel for the positive points and a channel for the negative points. And in general, what changes is the network and the strategy for the clicks. But this is what usually done. Some other works try to do evaluation time schemes, such as BRS. So the idea of BRS is when you have an output mask, it's not guaranteed that it's going to cover the points you clicked. So it's going to evaluate the model lots of times and change the parameters in evaluation time, not in training time, and try to make a mask that fits all the input points. But that's not good because you are going to evaluate the network lots of times, and this is going to be bad for performance. So we're basing a paper from 2021 that achieves the state of the art in 2 standard data sets, Berkeley and GrabCut, with the number of clicks to obtain 90% of ERU. And this 90% is important because in a paper from Google that makes a very practical approach, a large-scale approach to interactive segmentation. So they actually do an experiment in interactive segmentation with clicks. They achieved 90% of agreement between human annotators. So we are going to use this number as our objective. And it's also important to note that you can go beyond 90%, but it's just if you want to very specific high performance. And in the same paper, they show that if you use interactive segmentation, you are able, using neural networks, to achieve arbitrary performance. So if you want 100%, you can achieve it. The model is going to converge to 100%. The problem is just that how many points is it going to take for you to achieve this performance. So now talking about the requirements, we wanted something very, very fast. So the idea is to be the human reaction time for each click. So you click, you already have the results. And using the GPU, we are able to achieve sub 300 milliseconds, in all, taking into account all the service. So making the request, everything else. And you see that using this model, actually, we're not limited by the size of the image yet. It's almost a straight line. And if you use the CPU, you see that it's proportional to the scale of the image. And well, I'm going to follow. So that was the speed requirement. Regarding the ERU, we wanted 90%, as I said. And we defined that 5 clicks would be a good minimum requirement to achieve this 90%. And using our internal dataset that meets our needs, not a standard dataset, we're able to achieve this with at least 4 clicks here. Sorry, at least 4 clicks. And well, so that's just for showing the requirement. So what's different with our model is that we not just take as inputs the images and the clicks, we also take as inputs the previous mask from the model. So the previous mask is basically the model generates an output, and we input this output in the next step. So we made a click, it's going to generate the output. The output goes in the on-neural network. And so we take all these inputs, that's 6 channels, we convert it to 64 and send to a backbone layer. We used HRNet plus OCR. And this is going to output our masks. So these are the details about the network. But actually in training, there are also some things to speak about. Normally, what's used is distance maps for the encodings of the clicks. But it's shown that they're not the best encodings. We achieve better results by using just fixed site disks. And that's what we use. And also, when we train, we don't have the clicks in train time. We just have segmentation masks. And we have to generate these clicks. To generate these clicks, we don't use a random clicking strategy. The random clicking is just you have a mask and you make a click in a random position, then you make a click in another random position that's a little far away from the first random position. So we actually do a partial smart strategy for clicking, and the smart strategy is like clicking always in the middle of the greatest misclassified region. That's not the only strategy we use this and random simple. And finally, we don't use the normal cross entropy, we use the normalized focal loss. That's better for focusing on misclassified samples. So just to give you an impression of what the output from the model looks like. So we here made a click in the middle of the flower and generate something like that. And every time we make a new click, you see that the model gets more sure of what represents the flower and what doesn't represent the flower. And something that's interesting to talk about in this image is that, for example, if our client needs to select the whole flower and not just the middle of the flower, you see that here it selects the middle of the flower. But if you fine-tune the model with images where we selected always the whole flower, we can actually make it in the first click select almost the whole flower. So what I mean by that is that we have a model that generally you can use to select objects, but if you fine-tune for a specific purpose, you can make data annotation very, very fast. Just because the model knows more or less what you want to annotate. Something also we wanted to discuss is that we discovered that the model is very sensitive to the scale used in the training. So we try to train it with lots of datasets with average sizes vary. So here's some client data, Davis, which has fixed size images, and this one is the training, a substantial of it. And actually, when I'm going to show a plot just for Davis, we see that there is somewhere where, so here it goes from all the way from 20% scale, so scale is like in height and width, and it's a scale factor. We go from that to all the way to 300. There's somewhere where the performance is better, and so it's not arbitrary. You can't make all the way large, and you're going to keep performance out. We're going to degrade the performance. So seeing that, we have made it so that our service always rescale the images so that it always works ultimately. And you can say you can add images of different scales in training, but the problem is that we're not going to put all the scales there. So it helps make the model more robust because we're working with clients and we want the platform to work good every time. And now the previous mask. So we can actually input to the model a empty previous mask. So all zeros. And actually you see that a lot in the training data because if you made the first clip, you can't input a previous mask. But if you make all zeros in the input from the model, actually our performance goes very bad because actually I don't know because this is just the results we had. But actually what we get is that this adds some memory to the model. So it gets much more stable in time when we add more clicks. So what you see is the difference between both. And the previous mask, it's also important to emphasize that this is a matrix of floats. And here we study how can we do if we don't input just floats, you input constant values. So we don't have floats as an input, we just have a mask. And why that's good? Because you can define a mask just by a polygon. So you can compress the information much more. And so we studied different ways we can, so just to make it clear, the model has 3 inputs, the image, the clicks, and the segmentation mask. I'm working with the third one here. And usually the third one is a matrix of floats, which is the previous output from the model. Now we're going to input there just constants. Either 0 or 1. Then we pre-process that, in this case, multiplying by a constant. In this case, adding a Gaussian blur. And in this case, adding a blur plus information from the image. And we compare the performances here. And you just see that the constant value actually works very well. And it might be perfect well to use that if you want good performances for low clicks. If you add the blur, you get more stable outline. And this makes sense because if you see the images, the output from the model before, you see always that the edges are blurred. And in the end, this one kind of is in the midterm between both, but we didn't quite get good results for this one. And this is just what it looks, each one of them. So the constant value was the best one for us. Then the blur looks like this, and you have blurred edges. And this is adding information from the images. And the problem of this is also that you're going to have lots of variation from one image to the other. But the idea was that this might be good for detecting some edges, for example, here in the t-shirt, the short. Then now that's something that's very interesting. We actually try to see what fine tuning did. So it's the same idea of the flower. We had some very specific tasks from client data, and we wanted to see if fine tuning would help. And actually, it helps a lot in low clicks. So here we could achieve like 95% of performance, almost 96, but you get like 20 clicks, and you get pretty good results with 5 clicks. But if you fine tune, just 1 click is 90%. So it almost instantly understood how the images were annotated. And if you fine tune along with the labeling, you can actually build a model that improves over time in helping you annotate. So both improve together. And well, you get very good results for low clicks. But the end is similar. So now the last part, I didn't explain it a lot in the outline in the beginning, The idea is that with interactive segmentation, you can actually do better than with just using segmentation, because you get some extra information. Like you don't get the perfect information from the borders, but you get some extra information. It's temporal information from the clicks, and spatial too, because it's a sequence. So if you are making an annotation of this asset, so assets is an image, you're going to make a click and it's going to annotate something here in the middle, for example. Then you add a new click and it's going to make a new annotation. And then you can add a third click and it's going to continue annotating. And you can add also negative clicks. And what you get with that, you get a sequence of points, but not just points. You get intervals between the points, the time you took between each point. And you also get different masks. And you can make the difference between these masks. And for example, if I made a very good annotation, probably in the end, I made points that were very close and the masks didn't vary a lot. So using this information, I can now actually see which assets were better, or I can have an idea of which assets were better annotated. So that's an idea which was discussed in one paper from Google that we're based on. We didn't implement it yet, but it's very interesting because you can use these three informations here that I did just mention to train a regressor that's going to try to predict the AUU. So they just use a random forest, and they were able with this to make a distinction between the assets that were better annotated and that were worse annotated. And they classified by the output from the regressor. And actually, the ones that were in the bottom had a worse AUU, and the ones in the top had a better AUU. So this is already enough to make a distinction between assets. And visually, even you can see that, as I mentioned, if you see points closer and masks that don't vary a lot, this probably means that something well annotated, and something crazy like someone did this just 2 points and the masks varied a lot. It's probably not well annotated. So what's the conclusion with that? All that is that using this tool, we made a brief estimation of what we can gain. It's something from 10 to 2 to 10 times speed improvements. And this can vary a lot based on fine tuning. So you can make a direct improvement just by fine tuning the model to your specific needs, given that you make an annotation for a specific purpose. So you can use this actually to make image segmentation much faster. And if you do image segmentation very fast, you can actually even probably get faster than drawing B-boxes. B-boxes is 2 points. So if you can do like with 1 point, 90% and 90% is enough for you, you can get rid of boxes and you get a segmentation mask, which gives you actually more information than the big boxes, and potentially you get better performances with that. So that's something that's very interesting. You can do with that, because in most cases you use B boxes because it's very cheap and give good results. But with this, you will get the maximum you can. So you can, what we still have to do is add a prioritization for Keyless platform and study more data sets for training. Study if the model loses performance with fine tuning, which is probably true because, for example, in the flower example, if you want to select just the middle of the flower and not the whole flower, and you fine tune for the whole flower, it's going to lose performance in selecting the middle. So in conflicting cases like that, you can actually see that. But it's good to study how you lose performance, because this would affect how we distribute the model. If it's just a general model that's given for each client, or we make subsets of models. And there's also another thing is studying other encodings for the clicks. We did like fixed size disks, but we can do lots of other different stuff. We didn't explore that a lot. We can do, for instance, like varying size disks depending on the concentration of clicks, for example. But it's something we had to study. So that's it. Thank you. And well, we're hiring at Kiwi. And thank you for Sika to let me do the meetup here.
Thank you very much, Aloysio. It was awesome. Is there any question in the audience?
You're doing a meetup at Kili too, based on data.
So when is it?
It's next Wednesday, okay. And it's going to be presential too. So it's half presential and half.
Okay. Awesome. I think there is a question. Does your tool works with video?
Not yet. For now, it's just image, but I think in the future that's the idea, because in the platform we can annotate by hand video. As you have more information, I did not understand the more information part. Can you read it?
I think I have some questions.
Yes. Just to respond, is there any difference to put points inside an object or then close to edges? You're supposed to put the points in the middle of the, because that's what used for testing. And that's actually important to mention. When testing, we use a deterministic strategy, which is an algorithm that selects always the middle of the misclassified region, the misclassified region with the greatest area. So you're supposed to do this when you are annotating. You see the middle of the misclassified zone and you click on it. Yeah. Who was going to talk?
Yeah, that's me. What's the goal? What's the goal of your experience? What's the end goal? What do you want to? What's the outcome?
The goal was to, like, if you want to make segmentation masks, you usually draw them, and you actually in the current platform in the past, you draw them by hand. You can still do that, okay, but the goal was to do that faster. And we do that. You have the possibility to do that now by clicking.
Okay, good.
In the video.
All right, oh, it's interesting.
So you do it. So here, for example, I did a click in the middle of the car. Now I do a click in the street.
Okay, so here you want to annotate the road.
Yeah, I want to take the road.
I think we are okay with the chat. I have a question. Do you have many clients that use the interactive segmentation?
Currently, not just one client, I think.
Okay.
It's fairly new.
Okay. Did you try to measure how it works in production? Because you mentioned that you, in the test set, you have a deterministic strategy for generating the clicks.
Yeah.
But maybe it's not what users do. So do you plan to measure, you know, like collecting actual user clicks and doing the segmentation mass by hand to have the ground truth and see
Yeah, that's definitely something we plan to do, but we didn't do yet. We see that I say that we didn't do because we didn't do quantitatively, but qualitatively it works very well. If you click and you see the clicks, it works well, and the speeds are the ones I presented are actually using the platform.
Okay.
So the whole service.
Awesome. Do you have any more questions?
Yes. You mentioned that you were fine-tuning some models, and you were training on fine-tuning to like improve the number of click performance. Do you have with the plan to like automatically deploy and retrain models for this purpose?
Yes.
Great. Nice.
We're implementing that. What we don't have yet is the possibility to fine-tune a model for each client. So lots of different models working at the same time. But as we don't have many clients working with that now, we can easily fine-tune the model for the client that wants it.
Yeah.
Okay. And I had another question. Most of this strategy with superpixels and stuff like this, like bounding box and graph cut and others, tends to work by following the edges. Does your model tend to do the same, or because it's like a deep learning model, it doesn't choose directly this kind of feature? Will you be able, for example, to not only follow the edges of the car, but for example, ask to guess the place taken by the road itself and guess the way it is behind the car? Do you see what I mean?
No.
So like most models use superpixels and just like follow the edges that are naturally present with this kind of algorithm. Would your model work well if you didn't try to just follow the edges of like the car, but for example label the road like the car was not there? So for example, doing something like this. Because this can work with most like
label
methods.
This.
Yes.
That's what I mean?
Yes, like ignoring the car.
No, I don't think so. I don't think it's possible, but we are going to have to do lots of clicks.
Okay.
What it tries to do actually is normally follow well-defined stuff.
Okay, so it tends to follow which is also the same way that most models. Okay.
Okay, I think we have more questions from the chat. So, how many clicks do you need to annotate this image into 3 parts with 2 sleeves?
Which image? I have no idea. I cannot say.
We can see the image here.
Which image?
Somebody posted.
The link?
Yeah. Maybe. Oh wait, sorry, we can see the image. Maybe, oh yeah, it's this one. We can see it.
Just the annotate what exactly?
3 parts, so the 2 sleeves and 1 torso. So I guess this and these 2.
I have no idea. I mean,
somebody say about 10 clicks, maybe.
Did you make it?
Okay.
Okay.
So about 10 clicks, says Maxime. There is a question from Oleksandr. Is there any sense to apply similar approach to annotate data for object detection?
I think it's a good idea. If you want to see if the object is in the image, That's it.
I don't know.
Or
What do you mean
want
exactly, Oleksandr?
How?
What do you mean exactly by object detection? Do you think of bounding boxes or something else? Because bounding boxes, it's only 2 clicks. So.
Yeah, bounded boxes. Yes.
Yeah, I think it's that's a similar idea because the idea is to annotate an object. Bounding box is an approximation of the object. So if we can make it faster than the bounding boxes, definitely the idea is to use that.
Okay, thanks.
Yeah.
Are there any questions in the chat?
No. You can.
Just my question was about the images that you use to evaluate the performance of your approach. Would you describe the difficulty of segmenting those images, and how would you evaluate that? Like, were there easy images like the one we see here, where it's either blue or white, or were there complex images, and how would you evaluate that?
I would say that they have like hard to define regions, some hard to define regions, and they were completely different from the training data. Like,
okay,
they were very diverse in comparison to the training.
So like you brought them, they were client images.
Yes.
Oh, okay, okay. Okay, I see. But you don't have any like some kind of measure to evaluate how difficult they would be for the model to segment.
No, I don't think so.
But maybe what's going to be interesting now is that now that you have clients, you will see which assets clients find hard to annotate with the metrics you showed us. So you are going to do some kind of, I don't know, active learning or something like that, like choosing those assets to retrain the model.
Yeah,
make it better. So looks awesome. So
but I didn't find any asset that's particularly very difficult. By him, I can say that that's general.
Would it make sense to suggest points and on which to click to help the model the most at the next click?
What do you mean by suggest points?
From what I understood, clicking in a specific points helps the model much more than on another points when the user is annotating, right?
Yeah.
Would the model be able to tell the few location of the points that would help the model the most to decide between different options?
The idea is always to click in the middle of the region you think is the worst classified. So I don't know if it makes sense to.
Again, the idea is that how do you do to avoid having to train the people to use your specific tool in a different specific way of thinking?
Yeah, I understand what you mean. I don't know, I didn't think a lot about that, but the idea is that you should see mostly examples of what the model outputs, you know? Like, the main way to train, I think, is to try out the model, see what it generates, and with that, you yourself iterate.
Yeah, so the model trains the clicker to get better at using the model.
In essence, because when you're using it, you feel how it does, and you feel where it's better to click for it to perform better. For instance, for example, in the car, if you didn't click in the door, you might not get the whole car. you might get just like almost the whole car, but you would have to add a second click, and we wanted to get the whole car in a single click because it's better to show. But yeah, as I said, you can get a grasp of the model and try it.
Okay. I think that's it. There is no more question. So thank you.
Yeah. Before going, I have a question. Yeah, man. I mean, I'm not from a background of tech or anything. I just have something. If you had 30 seconds to pitch what you do, what can you say? 30 seconds, just 30 seconds.
Keely or the data annotation, the interactive segmentation tool?
No, I mean everything you presented, your company, what you do, and what you're trying to create. Just 30 seconds, explain everything in details so that I can make sure I got everything.
Okay, we try to make data annotation as simple and fast as possible.
Great, that's good. That's good. That's good. What is your company's name?
Keely.
Okay, good.
Yeah, we will put the slides on the website, on the Meetup website anyway. So thank you very much, Aloysio.
You're welcome.
Thank you everybody for watching us, and see you in two months for the next Meetup.
Okay.
Bye.
Bye.
See you.
Bye.
Thank you, guys.
Okay, bye. Thank you very much.
Bye.
Bye-bye.